Hi, welcome to this webinar on GPU sharing for AI at enterprise scale. My name is Jim Dowling, and I'm CEO and co-founder of Hopsworks. And I'm joined by Alex Ormenison, who's going to give a demo on some of the things I'm going to talk about later in the webinar. So the agenda for the webinar is I'm going to talk about how we share GPUs, and particularly around Kubernetes. And I'm going to talk about a framework for sharing GPUs called Q, which is a CNCF project. And I'm going to talk about how we integrate Q into Hopsworks and how you can manage GPU sharing within the Hopsworks platform, and how we then write and run applications that share GPUs on Hopsworks. And then we'll have a demo from Alex. But I'm going to start and kick it off by talking about some of the challenges we have with sharing GPUs. So one thing is that people nowadays, they often can purchase a GPU, and in particularly, we're gonna focus mostly on the sovereign AI case, where you buy your own GPUs and you're running them in your own data center, and we're running on Kubernetes. So I'm not going to talk too much about the public cloud. And one of the challenges when you buy your own GPUs is that you may often buy a GPU or a cluster of GPUs for serving large language models. And when you serve a large language model, you'll have applications using them to add intelligence to them, and to add a bunch of new nice features for your services and products. But the usage of those GPUs will inherently be spiky. Your applications will have particular usage patterns. Maybe they're busy at breakfast and busy at dinner and lunch, but not busy at nighttime. The inference will be spiky. And what we see is that you could have a dedicated cluster for inference and just buy a bunch of GPUs like Meta do with AMD GPUs for inference, but they'll remain unused at nighttime. And that underutilization costs you money because you've invested in this resource. So it would be great to make use of those GPUs when you're not using them for inference, for things like fine-tuning large language models and training deep learning models. So there is a chat question which just came up there. So you can ask questions in the chat functionality at the top of the webpage, and please go ahead and do that at any point in time. So you would like to have a cluster of GPUs to be used not just for making predictions or inference, but also for training. Now, a lot of HPC or high performance computing centers provide training as a service, and they do it on a resource scheduler like Slurm. So you could take a model, very large language model that you need to train, maybe even a foundation model or maybe some fine tuning, and you might use RAID train to raise a framework for distributed training. So training very large language models that even are sharded over multiple GPUs and that are replicated then over many GPUs to make training go faster. You can train them on a large cluster like Slurm, but when you want to do inference as well, so when you want to serve those models to applications, that's when Slurm will let you down. And that's where Kubernetes is the current star of the show. So Kubernetes supports many different operators for running many different types of frameworks. So you can run all of the machine learning frameworks from PyTorch, Ray, TensorFlow. You can also do large scale data processing that you often might need for large language models and for deep learning models. And also it supports serving of models at scale on frameworks such as KServe, which is an open source model serving server on Kubernetes. And a lot of use cases will involve batch inference, where you're making predictions on a schedule. Maybe you're writing a large Spark program. It's going to make a lot of predictions. Again, you'll need to use GPUs to do those if your models are deep learning models. So the challenge is when you have a scheduler that's going to manage all of these mixed workloads is that this scheduler needs to allocate GPUs to jobs. And those jobs, we can think of them as consisting of a number of workers. In the case of Kubernetes, those workers will be pods. Pods are a group of containers that get allocated together. So here in this example, we can see we've got 8 worker pods, all looking for a number of GPUs. They could be looking for 1 to 4 GPUs in this example. And our scheduler needs to allocate them to the resources available in our cluster. So we've got 4 nodes here. 3 of them have 8 GPUs, and 1 of them has 4 GPUs. So your scheduler in Kubernetes supports allocating GPUs two pods, and it's relatively functional, and it's been around for a few years, and it's improving all the time. So you can actually go down and add labels to your hosts in your Kubernetes clusters that support GPUs. You can install the NVIDIA device driver, and those GPUs become visible. And you can even set some priority space around labels to some of those nodes. So, and some of the jobs as well in namespaces in Kubernetes, but it's still missing quite a lot of functionality. And that's why the Q framework, which is a CNCF project, was initialized on Kubernetes, and now it's become a mature top-level project. So I'm going to talk a bit about Q as a way of scheduling jobs to GPUs on Kubernetes, and how we integrate it into Hopsworks. So the default Kubernetes scheduler, it takes a job, and the job is submitted to a workload controller, typically. And that workload controller sends pods to the default scheduler, which binds them ultimately to hosts or kubelets that run those pods. But there's a few things missing from this. So we're not going to, if we follow this approach, we're not going to optimize our GPU utilization. So for example, if I have a large 80 gigabyte GPU, a H100, or an even larger H200, but I only need 10 gigabytes for a model, I might get over-allocated resources. Maybe I have a job that needs 4 GPUs, but those GPUs are spread over different nodes, and when I deploy it, it's going to go really slow. I would have preferred those 4 to be co-located on the same host. Then we wouldn't have a network I/O as a bottleneck. We also want to make sure that certain jobs have higher priority than other jobs. So you may have a production training job that has to run at a particular time, and then you may have an experimental training job that someone's running that's lower priority, and an inference job might be higher priority, and so on. So you want to be able to have fine-grained priority setting for these different jobs. You also, in any large organization, so if you're a large enterprise that has many different business units, and some business units have dedicated needs for resources, you need to be able to give quotas to those. They're all going to share the same cluster because you want to optimize GPU utilization over your whole enterprise. But you want to make sure that different business units get what they need, and then if there's spare resources in the cluster as a whole, those can be allocated to those when they need them. So you can have temporary over-allocation of resources if they're available, but we also then need to take them back and preempt those resources if a higher priority job needs them. Okay, so that's kind of what's missing, and this is what Q provides and adds to Kubernetes. It layers on top of the default scheduler. It doesn't replace it. So when jobs get scheduled to Kubernetes, Q receives them, still sends them to the workload controller, which sends them to the pods and default scheduler as before. So you can mix in other workloads that maybe aren't supported by Q, and you can even set up a very large cluster where you say some of the resources are dedicated to Q with labels, and other resources are outside of Q and not managed by Q. What Q kind of looks like at a high level is that you submit jobs to Q, and Q logically puts them into these queues. Now, typically you might think, oh, these are priority queues. I understand this. This is priority 1, 2, 3, 4. This is the highest priority. This is the lower priority. But the queues are a little bit more complicated than that. We'll call them hierarchical queues for simplicity. I'll describe them more on the next slide. But the queues will basically be a way of deciding, okay, will these pods get scheduled together, or will they be scheduled individually? Which one has the highest claim or highest priority on the available resources at the moment, and does it fit their constraints? Should it be on the same host, or does this one need another GPU to complete its allocation, its requested allocation? And they're all going to deploy the jobs, or in effect the pods in this case, for training, inference, and even scalable compute on GPUs. They're going to be on the same shared platform, Kubernetes platform. Now, if you do have a case where you're running a job and the job has some GPUs and the job gets preempted, you need to be able to suspend that job. You need to be able to then resume it when the resources are available. So we'll see that there there's many frameworks that are integrated with Q, such as Ray, which is used for training and serving, is integrated into Q, so that if you're doing a training job and it gets preempted, there's a hook into the Ray operator which will suspend your job, And then when resources have been reallocated, it will be able to resume your job. So the queue is a scheduler for mixed workloads, training, inference, and scalable compute. And then we'll have a look at these hierarchical queues. So the way in which you divide resources within your organization in queue is effectively by thinking of designing something like this tree that we have here. So if we look at this tree here, we have a dev org on the left-hand side, and then we have this dotted line. And on the right-hand side of the root, we have an org n. So these are effectively two different boundaries. So everything on the right-hand side under org n are kind of shared, and the resources that are given to the dev org are not available to org n over here. But within org n, we have two different business units, business unit 1 and business unit 2. And they're able to borrow resources from one another and share resources with one another. So they can have dedicated resources. So business unit 1 has a certain number of GPUs it should always have. Business unit 2 also has a similar minimum number it should have. But if there's spare GPUs, they should be able to be shared between the different business units as needed. So that's what we look at. Now, at a high level, when you submit a job to queue, you're submitting it to a leaf node. So we have, in this case, I'm calling the projects. We'll look later on how these map into Hopsworks concepts. In Hopsworks, we have projects where we organize data and users, and you submit your job within a project. But ultimately, you'll get sent to one of these leaf nodes, which are called local queues in queue terminology. And this grouping here is called cohorts in queue terminology. And then these intermediate level nodes here are called cluster queues in queue terminology. But I'm not going to use that terminology. You'll be able to read up on it yourself. What I'll talk about is how we can share the resources across our organization here. So here we can see a situation where org n has a certain number of GPUs. We have 6 GPUs, 4 to business unit 2, 2 to business unit 1. And these are guaranteed resources to them. If business unit 2 requires the 4 GPUs, it gets them. And if business unit 2 requires 2, it will get them. But we can see that the org n has no access to the dev org's GPUs. They're separated. Now, let's have a look at what can happen. So in this case, we can see that Project C got 2 GPUs from business unit 1. Project E got a GPU from business unit 2, and Project F got 2 GPUs from business unit 2. And all of these projects can have different priorities. So if a new project arrives with higher priority, for example, if Project D comes in and it's higher priority than Project C, it can take those 2 GPUs and start using them because it's taking them from the business unit 1. But let's just assume we have a scenario where we've got 1 free GPU over here, and Project D, somebody submits a job. Now that is not a guaranteed resource for business unit 1, business unit 1, but it's able to borrow it from business unit 2. So we can take that GPU from business unit 2, borrow it, give it to business unit 1, and Project D starts using it. If a project in business unit 2 requests a GPU, it'll take it. So it'll have higher priority and take that resource back. But if it doesn't, then the user in Project D can continue using the GPU until they're finished. So that's called lending and borrowing. So we have the limits, which are the minimum amount you're supposed to each project can have, and then we have borrowing, where we can take within from different business units at this level. So these are what are called the cluster queues in queue, and queue also has the notion of fair sharing. So it's not first come first served. It's based on if we have multiple competing clients looking for the same resources, they'll be shared fairly rather than a first come first served basis. Now, I mentioned already that queue has the ability to pause applications and resume them. So we can suspend an array application, training a model, and then resume it. It does this for all operators. So you have Ray and Python and some other operators supported. Here we can see that queue basically requests a suspension of the operator. The user can see the user has submitted they've got a custom resource allocation for submitting the Ray job. In Hopsworks, you don't need to do that. You just submit. We'll see that you submit the job from the user interface. You're not writing custom resource definitions in Hopsworks. But your job, when it's being scheduled, queue is managing its life cycle then at this point. And it's allocating it pods, it's suspending it and resuming it, and so on. So another requirement that a resource scheduler can typically have in a Kubernetes environment is what we call gang scheduling. So if you want to fine tune a large language model, let's say you take Llama 4, and we can take the Scout model, which is, I think it's 150 billion parameters. You're going to need a few GPUs to train that model. So, or to fine tune that model. So in order to fine tune it, you'd like 4 pods, for example, each with a GPU, and we like them all to be allocated together. So I don't want to get 3 GPUs and then sit around waiting for the 4th. Just give me all 4 or don't give me any. So gang scheduling is also supported by Q. And, you basically, when you're submitting your job, you basically specify that this is a gang, that you need all the resources at once. Okay, so that's a brief overview of Q, and now we'll look at how it's integrated into Hopsworks. And the real reason why Q is interesting and why Hopsworks should be interesting for many of you is that, yeah, you can go and implement Q, but how do you then, build your AI factory on top of Q? You have to have training support, you have to have inference support, you have to manage data sets, you have to do feature engineering at scale. You may need notebooks and jobs and so on. And that's basically what Hopsworks provides, a complete data AI platform on top of the GPU sharing that we see below. So what Hopsworks basically needs to run is Kubernetes cluster and an S3 bucket. So typically you would have, a MinIO S3 store or something like that. It can be deployed with open source container registry. It'll typically connect to something like GitLab or GitHub or Bitbucket. But they're kind of the only external dependencies that Hopsworks has. Otherwise, Hopsworks can manage jobs. You have Python, Spark, Ray, and so on, jobs that are submitted and run on GPUs, CPUs, and they can give memory. So Hopsworks is general purpose compute. There's also large-scale data storage with Lakehouse tables. So that's Delta Lake or Apache Hudi. And then there's real-time data support in our database RonDB, which is a fork of MySQL cluster, and also a vector index for RAG support in your large language models. The other things that infrastructure that you need when you want to build and operate AI applications are you'll need a model registry, you'll need somewhere to serve your models. Hopsworks supports KServe and vLLM. And it also has a feature store, so the preeminent feature store, which it manages your features for training and inference. And then when we move higher up in Hopsworks, you can run Jupyter notebooks inside Hopsworks. There's support for Airflow, and there's also support for an LM engineering assistant, which is coming out very soon. So, what I didn't mention, I mentioned at the beginning, is that what if I have a big GPU, let's say 80 gigabyte A100, and a lot of the training and inference jobs I have only require 10 gigabyte sizes. What you can do is you can partition that GPU up, 80 gigabyte GPU, into 8 MIG devices. So MIG stands for multi-instance GPU. So Hopsworks supports MIG devices. So they'll just look like GPUs, like any other GPU in your cluster. And you'll typically have them labeled as 10 gigabyte GPUs. So when you're requesting them, you can say, I want the 10 gigabyte GPUs. And the only thing that at the moment that hasn't been released yet is dynamic MIGing, and that work is ongoing. So how do we map the queue concepts into Hopsworks? We looked at hierarchical queues and hierarchical queues within Q, but in Hopsworks we don't have a hierarchical project. Everything in Hopsworks is organized by projects, and it's a flat namespace. You could have a project which has all departments, so everybody in your whole cluster would be a member of it. But then you may have different projects for different business units. And what we'll see is that these are all secure sandboxes, but they can share data between them in a controlled manner. But from a Kubernetes perspective, each project has its own Kubernetes namespace. So we'll see that we use that fact that each project has its own namespace to submit jobs within your namespace. And Hopsworks can then assign priorities to available priorities for jobs within a project. So if you have special victims project, for example, and that's allowed to submit low and high priority jobs, and then that maps onto the Kubernetes namespace for this project, and that's how the project is given that priority when you submit it. Okay. Also quotas, because Q supports quotas, you can define them again at the project level within Hopsworks. So a little bit more detail on what a project is in Hopsworks. I said it's kind of like a sandbox for private data that has members in it. The other thing that it has, so it's not just, there's a copy of it, it has its own local feature store, its own model registry, its own KServe, and even Kafka topics, but also unstructured data. So if you're working with, text or image or video data, you can have, massive amounts of that data private to your project. For GPU sharing, each project has its own GPU and storage quotas, which is you can set at an administrative level, and also you can set the available priorities for jobs for each project. So this is when a user submits a job, they'll be able to say, okay, this is a high priority training job, or this is a low priority experimental job. Projects also implement something called dynamic role-based access control. I think it's easier to explain with an example. So if I'm running a RAID training job inside this project called Cyber, it's not going to be able to read the data that's in the other project, narcotics, over here. And even when Alice is a member of both projects, her RAID job won't be able to read from the other project. And similarly, a notebook that she starts in the narcotics project can't read back in the Cyber project. And they're really separated from one another because each user each Alice user in each project has their own identity, their own X509 certificate. So this is when you run a job in one project, you lose the privileges to access resources in the other job. So it's role-based access control, but it's dynamic depending on the context in which you submit your jobs. But you can still share data across these projects if you need to. So you can say, okay, the data in this feature store can be shared from Cyber to narcotics, but shared with read-only privileges. And you can do that at the table level or even at a view level, which enables row-level access control. So how do I build an application then? Now that we've talked about managing GPU resources with Q, how we map that onto projects and Hopsworks, how do I build an AI system, whether it's a training pipeline or an inference pipeline, or just the application that uses the inference system? So we're going to look at how we organize AI systems as what we call feature training and inference pipelines in Hopsworks. So typically when you want to build an AI system in Hopsworks, you don't build all the infrastructure we talked about. You just write a feature pipeline, a program that will take your raw data and transform it into the features that you want to use. So if using large language models, maybe you're going to be doing chunking of your unstructured data, your PDFs, and writing it to the vector index. You'll have a training pipeline. Maybe you'll have an instruction data set. You're fine-tuning your large language model here. You're saving it back into Hopsworks, and we can save the largest large language models into our model registry because we have file system support for this. We'll talk about it later. And then an inference pipeline, whether it's batch or whether it's an online model with KServe, this will read again from the platform. So these are three ways in which the three programs you write to make up your AI systems. We'll have a quick look at them, starting with the data source. So Hopsworks supports tons of different data sources. I won't go through them, but basically any kind of any common one that's out there is pretty much supported. The next part is the feature pipeline, and typically feature pipelines will be written either as batch programs that run a schedule, so Pandas, Polars, Spark, DuckDB, or streaming programs that run 24/7, so Flink or Spark streaming. Training pipelines, again, Hopsworks is open. We're not like some frameworks that force you to use one or two frameworks. It only supports Kubeflow. You can run Kubeflow in Hopsworks, but you can also run RayTrain or PyTorch or TensorFlow and so on. And then for inference pipelines, for online inference, KServe vLLM is the most common, particularly for large language models, but maybe you're serving just a Torch model, TensorFlow, or even XGBoost. They work fine. So that's your responsibility. You build these ML pipelines, and that's your AI system. So when you're actually running the training jobs or the inference jobs, you come into Hopsworks here, and you can see what resources are available. Here we've got 4 GPUs free. I'm going to start a Jupyter server, and then I can claim 1, 2, or 3, or 4 of those GPUs. I can see what labels are available to me in my project. It's this dedicated machine, or then I can also see if I'm what priority levels are available to me. So basically, you select the resources you want to have. When I'm running a training job or an inference job, I need to have some base set of libraries that I want to run with. So Hopsworks supports what we call automatic containerization. We have some base containers. So if you're doing feature pipelines, there's Spark-based feature pipelines or Pandas, Polars ones. If you're doing training, it could be Ray, or it could be Torch training, or Ray Torch training, or Pandas for XGBoost. And then for inference, you'll have, KServe, vLLM pipelines, and so on. So you pick your base container, but you may need to customize it. So we have a user interface where you can just install libraries that you need for that base container, or maybe Python libraries. So it could be an operating system library, you'll do an apt install, or a Python library. And then we basically transparently build and register these containers for you. So when you want to run your job or your notebook or your model deployment, you basically select the container that you've customized, and you request the resources, the GPUs you need, and off you go and run the thing. So this is you're not writing Docker files, registering with a Docker registry and a container registry, and then running them. We really make it much easier for developers. I'm going to conclude by looking at how Hopsworks handles scale, which is a massive challenge, particularly in large language models. So this is just showing you a kind of a typical setup for training large language models at scale. We've got GPU server 1 and N, and they're connected by a high performance, 400 gigabit or 50 gigabyte per second network. We've got an object store down here. And then we have other places where we can have bottlenecks. So here you can see a local copy of the data that's in our object store on NVMe disks, which gives us much higher throughput than available over the network. A nice PCI 5 bus to get the data from our local disk into the GPUs, and then a GPU bus for all traffic between the GPUs. Got 8 workers on this GPU server. And we're using ring all reduced to do distributed training here. So what I'll do is, how do we debug and find low GPU optimization or utilization levels? Here you can see you've got quite high utilization levels. But here's one area where we have some really interesting technology in Hopsworks, which is preventing slow training or low GPU utilization due to disk I/O bottlenecks, and which is very common. People put their data in S3, they start training, and then their utilization levels are lower than 10%, and they don't know why. So what we do is we support what's called tiered storage. So you write your data to our file system, HopsFS, which is a HDFS API. The data will ultimately be stored in S3, but the most recent blocks will be stored on NVMe disks at servers. So that means that when you go and write your data in your feature pipeline, you create some instruction data set or some other alignment data set, it'll be stored in the NVMe disk. So when you go to read it up again, it will come back at NVMe speeds. So that can mean the difference between 200 megabytes per second on S3 to 8 to 12 gigabytes per second on NVMe disk. So it's a massive difference, particularly, for example, loading a large language model. So if you have a large language model you've downloaded like DeepSeek, which is 100 gigabytes or more, and it's only a small number of files, reading it from an NVMe disk via HopsFS is much faster than reading it from blob storage. So we have tooling to help you find the cause of low GPU utilization, starting from the GPU. We have support for Grafana. You can go down to the PCI bus, the NVMe layer, the network layer, and storage layer, but I won't go into too much detail on that now. So I'm going to hand over to Alex, and this is in fact a pre-recorded video, but he's going to show how we support Q in Hopsworks.
Hopsworks has support for Q now. In Q, you define the queues at cluster level, and they're called cluster queues, and they can be grouped in cohorts, thus giving you a one-level hierarchy. Queues within a cohort can borrow resources from each other, but this borrowing of resources cannot be done across cohorts. In order to provide access to these queues for a namespace for a Hopsworks project, you create local queues and you assign those to the namespace. So for example, in this observer project, if I go to jobs, I see that I have access to 4 queues: production 1, production 2, production 3, and an innovation queue. Each queue has a nominal amount of resources, as we see here: 4 cores, 16 gigabytes, 2 pods. And all of these 4 queues belong to the same cohort in this case. And this means that they can borrow from each other. They are configured in order to be able to borrow the whole amount. So for example, in here we have 4 plus 2 plus 2 plus 2, so 10 cores, which tells me that each queue can borrow the other queue's amount. So in this case, 6, 2 plus 2. For this one, it can borrow 8 because the innovation has 4 queues defined. And you can assign each of these queues to different projects. So for example, production 2 only has access and can only view production 2 queue. Production 1 project can view this queue, production 1. But observer, I set it so that we can see all the queues. And I will leave the observer here as we start jobs. And for jobs, if you create a new job, there will be the option to set the queue that you want. In this case, you can choose from production. If you're in observer project, you have more queues to pick from because this project has access to more queues. And if we start a production job, and this job is just a sleep job, so we can see the status of the queue. I start the job. The job will go from initializing to eventually getting scheduled. And it's running. If I go to the observer, I see that this production queue is using all its cores. It has some memory left, but no cores, but it says it can borrow, right? So now I can start 2 more of these jobs. And the observer will see that now this queue is borrowing 4. The borrowing amount has dropped for all the other queues because they are all in the same cohort. So, for example, this queue doesn't have borrowing capability anymore. This one can still go and borrow 1 more, and it can go to, actually, yes, and it can borrow 1 more. And at this point, all the resources from the cohort are being used. If I start yet another one, this job will end up being queued and will stay in queued until another job finishes. So, for example, if I go back again, I see that this particular queue is fully utilized. The rest, actually, it says they are free because if this particular project wants to start something in this queue, it still can use these 2 queues and it will evict someone from here. But if the job is queued and doesn't start at the moment within a minute, the job will get stopped. But if I do stop one of the jobs, this other job should be able to get its resources and start running, and it will run within the same amount of resources. And once the jobs finish, the resources are released. How does this look like? So we define a number of queues named team 1, team 2, team 3. All of them are in the same cohort teams, so they share the resources. And the preemption is within cluster queue low priority. This means that as a last resort, if this queue cannot borrow other resources to run the job, it will try to preempt jobs within its own queue with a lower priority. However, it also has the reclaim within cohort to any. So as long as the queue is under its nominal quota, if it wants to start a job that fits within its nominal quota, it will preempt anyone and get those resources as those were like guaranteed to this team. So in Hopsworks, we have, like I said, a number of teams. Each of them is a project in here. And team 1, for example, has access to queue team 1. Team 2 has access to team 2. If team 2 wants to create a new job, for example, it will go here. It sees team 2. However, you can assign multiple queues to some specific project. We have team observer, which sees all the queues and can use all of them. So this specific team could use any queue, and it also sees the utilization of any queue. Okay. And to make this easy, we will keep the observer open. But now, as I said, the cohort is empty. The cohort has 2 plus 2 plus 2, so 6 cores free. We will look at only one resource, since this will be, in this case, the limiting factor. We define the jobs in each of the teams that so that they use 2 cores. So this each team can run one job in its own nominal quota, but the cohort has 6, so if no one's using them, one particular team can ramp up to 3. So team 1 goes in, sees the clusters or their specific cohort is empty, and they go and say, I want to run 3 jobs. And all 3 jobs will eventually get to running. Yes. So they're running, and we see that they are borrowing resources. So they're in particular borrowing 4 cores. Now team 2 says, I need to come and run something too. So team 2 wants to run their own job. And team 2 should now have priority over their own, like this is below their nominal quota. So they will preempt the other team to get their space that was reserved for them. However, if they want to run another job, they will have to wait for team 1's job to finish, and this will get queued. So the status is the same. But again, this is queued, but team 3 comes in, and they're also entitled to their own nominal quota. So they start a job. Their job will start even if team 2's job is still queued, because they have the nominal quota that they're guaranteed, so that we can get to a status where each team is running their own one job. So for the production queue, we will probably add most of the resources and set it up so that the other queues, experiment and innovation, can just borrow from this cohort, but their nominal values will be quite high, and they have the like highest preemption policies. So last resort, it can preempt in its own queue lower priority production jobs. If it's below its nominal quota and someone else is borrowing those resources, it will preempt anyone to get those resources back. If it's above its nominal quota, so it would need to borrow, but those resources are already borrowed by someone else, it will preempt lower priority jobs in order to get those and borrow those resources itself. How does the experiment queue look like? Or pretty similar, but maybe we reduce the reclaim within cohort to lower priority. So if it's below its nominal, it should be able to preempt lower priority, so that if production, for example, is borrowing the resources, it won't preempt production jobs. How do we configure the innovation queue? Well, the innovation queue would have very little resources, maybe not, maybe even lower. And it relies, like I said, on borrowing. And it has almost no preemption rules also. It can only preempt within its own queue lower priority jobs. So it can't preempt outside of queue. Even if someone else is borrowing its resources, it won't preempt that job. You can define these, or you can split and assign these queues to different projects. For example, project A dev could have access to innovation and to experiment, and project A could have access to all 3 of them, or maybe just production, depends on the setup. Now, if the cohort, right, so the cohort has at this point 2 cores plus 6 cores, so 8 cores in total. We will look mostly at the CPUs to see how the jobs will get assigned. Each job uses 2 CPUs, so we can run at most 4 jobs within this cohort by borrowing resources. So if the cohort is empty and no one's using anything of like from the resources of the cohort, let's say innovation comes in and says, I want to start 3 jobs. It's going way above its nominal quota because no one else is using these resources. Right. All 3 are running. We go back, we check, and we will see that innovation is borrowing 6 cores, so it's using above its nominal. Now, however, experiment comes in, and experiment at this point says my nominal quota is not used, and there are actually those two free. But experiment wants to start 2 jobs. So this means it will preempt one of the innovation queue jobs because it has that right. So we go in here and we'll see this should update soon. Yeah. So experiment preempted innovation and borrowed those resources itself, right? But now all the resources are used. So production says my nominal quota is not used at all, but my resources are borrowed by the other 2 queues, but still I want to run things. And since production is the highest, let's say I start 2 of them, they will preempt the other jobs and just run because they have the highest preemption class and they can preempt anyone, right? So it's using 4 out of 6 and it preempted the others. When we configure a cluster queue in Hopsworks or in queue, the fairness part, the configuration part is this fair sharing weight 2. We have defined a number of queues, prod 1, prod 2, prod 3, and innovation. They're set in the same cohort, so these resources are shared. So the whole cohort has 2, 4, 6, 10 CPUs. And like I said, there is this weight, which for the purpose of the demo, we are showing the weight and the borrowed. Now, Q as the framework for scheduling is using a formula to flatten memory, CPU, GPU pods that is borrowed by this queue into one flat number, into this borrowed number. Now, this number is also, the final version of this number is divided by 2, or the formula, right, is divided by 2. So if I start 2 jobs that are equal sized in pod 2 and pod 1, the final borrowed number will be half because of this weight. Now, this borrowed number is important because Q will consider, we give priority to queues that have a lower borrowed number. So if something needs to be preempted, the higher borrowed will be preempted. If something needs to be scheduled, the higher, the lower borrowed number will get to schedule its job. So this is the mechanism that ensures that borrowed resources are equally distributed among the queues, but they are this equality can be skewed by this weight, so that this gets twice as much borrowed resources, for example. Okay, so this has nothing to do with the size of the queue itself. It only looks at the borrowed resources. This is a score, let's call it, for borrowed resources. So if we go to prod 1 and we start 2 jobs, each job will use 2 CPUs. Okay, and we also do the same for prod 2. We start 2 jobs, each of them using 2 CPUs, 2 cores. Sorry. We go in here, we see 2 cores used, or 2 cores borrowed, so 4 in total. And I define the jobs in here to be the same. So they use the same memory, same GPU, same number of pods. But like I said, the final value for the borrowed is half for this queue because of this weight. So at this point, there are 2 cores left because there were 4 plus 2 plus 2 plus 2. So there's 10 cores, and currently 4 used, so 8. If we go into innovation and start 1 job there as well, we will fill up the queue, the cohort size. So at this point, with innovation, using the cores, the whole cohort is fully utilized, at least from the CPU perspective. So if prod 3 comes in and sees, hey, I have 2 cores free of my nominal. Again, I should be able to use these. So I will go in and I will try to preempt someone. Innovation is within its own quota. It had 4. It's below its it's below its nominal quota, so it won't be chosen for preemption. These 2 will be chosen looked at for preemption, and the higher one will get picked for being preempted. So if prod 3 goes in and tries to run a job, it will preempt this job. Okay. If we reset and we kill job 3, prod 2 will get its resources back. Okay. So again, from who gets preempted, from the fairness perspective, this factor is used to ensure that the one that's borrowing the most gets preempted. However, what happens when prod 1 and prod 2 want to start new jobs of their own? So prod 1 wants to start a 3rd job. It gets queued. Which one's running? Prod 2 wants to start a new job, and it gets queued. Okay, so both queues now have a pending job 1. Why isn't one preempting the other? As we've seen, if this job gets preempted, its borrowed goes to 0. And if this job would get to run its job, it will be 150 versus 0. So this will, Q is looking at both the previous state and the next state to be fair. So at this point, this would borrow more, but if this gets preempted and the other one gets scheduled, this will borrow more. So this is a case in which, even though they're not equal, there isn't a better, more fair state that Q can get into. So, however, if we do go to innovation and we terminate that job as if that would finish, out of these 2 pending, the lower priority one, prod 1, would win again for fairness, from the fairness perspective. So innovation goes in. Let's say we simulate that the job would finish, and then prod 1 should get the resources, yes. And prod 2 is still queuing the job. We will use the following setup. There are 3 teams in here. Each team has a nominal quota for CPU of 2 cores, and all 3 teams are in the same cohort, so they share these resources. So the cohort has 6 cores. The jobs in the team 1 that we will use each job uses 2 cores. So team 1 can borrow and run 3 jobs in total, so borrow for 2 jobs and 1 of its own. Now if we go to team 1 and team 1 wants to run its own jobs, it can start 3 jobs, as this is the size of the cohort that it's part of. And the 3 jobs are started. However, if it starts another 2, for example, they will get queued because the cohort is full at this point. If, let's say, one of the jobs finishes, then the first submitted queued job will eventually get the resources to run, right? And this will run. However, currently the system is configured to time out jobs after 1 minute, but this is configurable. So if we look at the status of the queue, so the team 1 is borrowing, there's 1 job in pending, and this job will time out after 1 minute for this specific demo, but it can be set to, it can be configured by the user. So if we wait 10 more seconds, soon enough, this job should fail with a timeout. Yep. So job failed, queue timeout.
So that was the demo of Hopsworks and the new queue functionality. It's been available since release 4.2 of Hopsworks. You can try out Hopsworks. You can install it at the moment we have an installer for the main cloud, so AWS, Azure, GCP, but also OVH cloud. It's a command line utility. It'll run the Helm scripts for you as well. If you want to install it on your own Kubernetes cluster, we have a startup license, and then we have another sort of broader enterprise license. But you can just reach out to us, sales@hopsworks.ai. We'll give you, access to a cluster that you can, or access to Helm charts so you can install it and try it out. If you want to learn more about Hopsworks, we have this book, Building Machine Learning Systems with Feature Store Batch Real-Time LLM, that I'm writing. Most of the chapters are available for free at the moment. And you can join our Slack if you want to ask us questions, which is available here, public-hopsworks.slack.com. So thanks for sticking out, and hope to hear from you all in the future. With that, have a great rest of your day. Thanks. Bye.